Good day, everyone. I hope everyone is doing good today. And I just wanted to take this time to say hello to everyone. It's actually been a while since I've actually been behind the camera to say hello with my face. You know, I'm still alive. It's not someone generating an AI version of me, as some people have been saying. It's kind of long story. But anyways, just to clear that up, I'm still well and I'm alive. Hello, everyone. This is really me. And with that said, it's a little bit of perspective on what it is I'm working on here. Some people may have wondered why, after talking about the capacitive displacement generator, it seems like he's taking some steps back. You see, I better explain myself here. Especially since the formation of the new company, the goal here has essentially become trying to figure out here the fastest way, the most efficient way to charge a big capacitor at extremely high voltages. Now, of course, I could take the hard hammer approach and just build a traditional Tesla coil off the 60 hertz mains with mechanical switching and spark gaps, you know, that's going to use just like Tesla coil, just like Tesla did. But built exactly like he did it, those things, as you know, are not low power devices. So if you're consuming essentially kilowatts right off the start, it may linger the project moving forward. So my goal is, okay, a capacitor essentially doesn't care where the charge comes from, right? As long as there's a charge. So whether it comes from lightning or the earth or batteries or a hybrid or a Bedini or a Tesla coil or a Don Smith like devices, as long as we give the capacitor that charge. Now, of course, what I want to do is exactly like I talked about in a video that's essentially so controversial, is that video of the displacement current generator that everyone is so talking about lately. So this is the one that I want to focus on ultimately near the end. But you see, and I'm sure most of you, as for the example, I use very low power and very small capacitor values and low voltages just to demonstrate the core effect, right? But for commercial quality power, where is our goals here, you would necessarily, like Don Smith knew, you step the voltage up drastically. So when you're dealing with charging capacitors or a capacitor at thousands of volts and then discharging that, this is where the big current comes in, right? So essentially, I need to figure out now. It's nice that we have a plot for a displacement current-based recycling mechanism, right? That's great. But once you get into thousands of volts, especially big capacitor values, something's got to charge that capacitor first, right? You can't just go abracadabra, then the thing just starts on its own, right? So big capacitance at very high voltage will require significant energy to be put into the input before the whole thing starts, right? So you got to be, and even to maintain it for of course, whatever you're going to have along the way, there's going to be minimal losses. So let's say you lose 10% along the way, you have to be able to provide that additional to keep the system going. So essentially here, what I'm trying to do is find out how to do that in the most efficient way. Less current preferable, but again, up to a certain point, right? If at the end of the day I find out that it takes 100 watts to get 1 kilowatt out, so be it. But the point is to figure out the less that I need to trigger the most intense effect to charge that very big capacitor. So it's not just going to be a quick charge. What I'm trying to say is it's not going to be quite as simple as determining the charge is going to be there, because it's very high voltage. So it's going to take something to charge that capacitor and maintain a bit of a charge, right? Even if if you look at my process, the system is able to recycle itself, but you still need to keep an independent input giving you like 100 millivolts to keep the first capacitor fully charged, right? So obviously along the way, if you've got a tap on its own inverter charging an auxiliary device, you could grab, that's the point I was making later on, that you can grab it from there and then essentially make the whole thing self-loopable. But of course, things get more complicated at super high voltages. So this is where I'm trying to figure out here, fastest way to deal with this. Once I've figured out how to charge them, so I'm thinking right now, I'm just experimenting with Don Smith-like devices, Bedini-like devices, Tesla-like resonance. I just want to analyze several possibilities here and figure out which one charges the fastest. Now, essentially, to start here in my kitchen, I don't want to kill myself. When you get into the very, very high voltage, high current stuff, you need specialty ground faults and emergency breakers and that sort of thing in a commercial environment. We're actually working on that, folks, but it's still, some months away. But until then, I still want to experiment and confirm some of my own theories and what others had. So on a small scale, I bought basically very small neon, basically toy version transformers to be able to see if basically instead of dealing in the watts, if we could observe the same effects in the milliwatts and then see if I can enhance that. So essentially none of this is going to be the final product, but it's to do my research and development to figure out how I can charge that capacitor as fast as I can, preferably in all indicators point that high frequency essentially is the way to go. But essentially, how are we going to drive that high frequency? There are several mechanisms that we could experiment with and hybrid one into the other. So as I move along, this is what I'm working on. So right now, some surprising findings. I'm trying to replicate a Don Smith-like setup here. And a problem I was having, and what most people have in this stuff, is it's not so much the magnetic field that gets in the way, it's the super intense E fields, which end up being capacitive. So they end up surface charging everything nearby at high voltage, right? Including your integrated circuits, your transistors, your switching devices, your computers, your Arduinos, anything you're trying to run to control any of this eventually goes kaput. Unless you have a very specialized, specific industrial way to essentially shield this. And for the moment, with my experimentation and what many others, we don't have. And people eventually get fed up of blowing equipment, especially switches and things like that. So it happened again the other day, just the one in my video that I showed with the neon transformer. I already blew that just from the, not a current thing, but the intense E fields cause electronics to go ugh. So I figured I still need to experiment, so I will show you how I did it. For basically the first test here at this one here, I try to turn on with the neon transformer, and I'm measuring with my meter here for the magnetic and the electric fields. And Don Smith talks about how it's mostly primarily a magnetic resonance transfer kind of phenomenon. So here I am, I'm looking for very strong magnetic fields, and I'm nothing to very little. But very strong E fields, as I suspected, capacitive coupling, anything nearby gets zapped, and essentially this matches with Don Smith's description when he demonstrates the capacitive plate, not in a traditional capacitor sense, but how he charges. It's a surface electrostatic effect, one plate and the other mirrors it, and you can use displacement current against the ground, for example, and as long as the frequency and the energy is there, you can continuously discharge that, and through displacement current get a modest power out of that. And this is what, as an isolated thing, he was showing. Now, what it is here is very interesting, because as Don Smith described it, now you see, perhaps it's because I'm running very low power in relative. Again, I didn't want to kill myself, so I'm starting at very low power. So part of this might be because I don't have the watts field to generate the magnetic, but I would think even in the milliwatts it should be enough to trigger something. But I wasn't really getting anything, especially with the digital switching, even with the high frequency, unless I added a spark gap, which introduced a lot of noise in there, and then I was able to detect a very weak magnetic field, but it was there, but again, still the E field mostly dominating here. Basically,
the opposite of what Don Smith was saying was happening. Not that that's a bad thing. I could take advantage of a E field as much as I could take advantage of a magnetic field, folks. It's just, it's like Don Smith may have been describing, like his description was wrong, but what the effect was is right, you know what I mean? I don't know. I'm still trying to confirm this part of it. So anyways, the problem I had was all my digital, any kind of switch would go bonkers with the strong E fields. So then I decided to take a step back and do the Tesla-like approach, but a more modernized version. The military has these things here, which I decided to use as my driver. So this is actually a military device. I have a few of these, and they are actually a precursor to a inverter. So you feed them 24 volts DC, they give you mechanically 60 hertz, 50% duty cycle with a built-in 110 volts pulse DC output, all mechanical, right? Which is very remarkable for that age and day. But this basically was military application, so it was made for in the field during harsh environments, exposed to high fields. So essentially, you were able to feed basically 110 volts to your modest. Like this could have been used for radio and communication, to control the heater of rectifier tubes, for even magnetic amplifiers, for the control winding at 60 hertz to get very high voltage and current output for their radar tubes and that sort of thing, right? So there is multiple usage for this, and what's very fascinating is there's also taps for additional isolated switches. So not only do you get pulsed 110 volts AC out, but you get additional prompts where you could use. So essentially what I'm getting at is I'm using this as a driver. It replaces the spark gap because these are like relays, very noisy. But it drives my neon transformer at 110 volts like it likes, energizes my primary coil here. Spark gap here is very unique. So I have this to a rectifier for now. See, this is the the secondary coil right here. So what was really fascinating is to confirm that there was a very weak magnetic field. I had this side and that side connected to a rectifier. And I could only get a few volts, but the E field was zapping everything nearby. So I said, okay, so it's probably capacitive. So that's why I have one leg on this side to trigger. So what I'm getting at is what's happening here at high frequency is Don Smith's effect. Coils at high frequency, high voltage, behave like capacitors as well. So this is becoming your capacitive plate like Don Smith. It's like he was cryptic about his message, you see? So it looks like a typical secondary winding, but it may have been, in part, a capacitor that mirrors, because we're passing the voltage right here into our primary here. It's very close. So it's energized with the field. You see what I'm getting at here? And what's happening is being capacitive on one wire, just like displacement current, you can discharge this through a potential difference. Don Smith was using ground, but in my case, to simulate it, see on the output, see what I got here is on one side of the neon goes into the one side of the primary here, and on the other side of the primary goes on the spark gap. The spark gap has a 1 kilovolt potential difference. So this is creating a potential difference to my rectifier tap here, one side of the AC, against the capacitive side here. And for some reason, just like that, it was modest. All of a sudden, I was getting maybe 10 volts on here. But the real magic started happening when I added this LC circuit here and I started adjusting. All of a sudden this went up to like 70 volts when I energized it. And with the help of an LC circuit to create a kind of LC resonance, when I measure in here, all of a sudden the E field dropped drastically and the magnetic field was all of a sudden through the roof. And this thing was charging very good now. So I will demonstrate that right now to show you folks. So right now on the voltmeter you'll see 0. because I've discharged it. Okay, so it's very interesting. So you only need 24 volts, basically half an amp, to run all of this. So considering it's running the switching, it's running this, it's going through this, it's energizing the spark gap, there's a lot going on, so it's not bad. You know, like the Bedini setup, some of the stuff took like 1.5 amps. So again, half an amp is not bad considering it's all analog, right? And this way here, it's robust. It's foolproof. Fields don't interfere with it because it's mechanical. It's basically the first half of a motor in here. And that's how you're getting your pulse. And it's also generating it's helping generating high frequency energy. So I'm going to plug that in. Trying to do it with one hand here. So there it goes. You can hear it. That's the vibrator. So you can see the spark gap here. That's creating the potential difference. And look how we are over here. 59, 62. So this is not bad at all now. And to show this is real, let's discharge it. Yeah, that's real all right, see? So let's do it again. See that? And it charges up pretty fast, because you can see right here we're already up to 26 volts. And I had to tune this, and all of a sudden this started climbing really fast. So what I did is I put on one side is the LC circuit in and out, and on one side of the rectifier. And with this whole setup so far, and I'll show you here. So this is, let's go to U Teslas. See how it's pretty intense? I don't even have to get like right next to it no more, and it beeps. And out here too, look. So now I'm going to go to the electric field, volts per meter. And it's nothing like it used to be. I have to get really close to it, and it's still 500 volts versus 2.5K, several meters away. So I just distanced like half a feet away, and I'm down to. So the E field is very low now, and it's mostly because of the LC circuit. Let's go back to the U Teslas. See that? It's stronger magnetic field now. It's the magnetic field now, as Don Smith said, dominated. But the mechanism that gets us there, so far anyways, is the opposite of what Don Smith claimed. So again, this is very early on, and it might be just because I'm limited. Everything is half an amp or less. Maybe you need wattage, like several watts, to get the full Don Smith effect. But from this specific experiment anyways, it's working basically as Don Smith says it would, but the mechanisms are not exactly how Don Smith explained it. If you can understand after what I'm showing you with the magnetic and the electric fields. And at first I was getting nowhere with this until I added the LC circuit in there, and all of a sudden it worked. But I still depend on the spark gap here to create the potential difference. See where we're up to, this thing keeps, it's at 105, 106 now. So we could discharge it again. It's already up to 24 volts there, 25, 27. So fast rebound this method. So what's very interesting here is maybe, and people were wondering about, maybe this is it, maybe this isn't. I know most people say that Don Smith, especially the cooler device, he used a series of diodes and gas discharge tubes, so is the rumor, and just fed that into a simplified inverter filter device. But perhaps it was something like this, and the spare ports here, you could send an isolated system. So the cap here, this could be used as a cap dump at 60 hertz, you see what I mean, into your load directly, as long as you got the right voltage. So given this thing is going up to like over 100 volts, with the right setup, the right scale, right, the right tuning and everything, this could maintain a load completely analog, like a cooler, a fridge kind of thing. And what's interesting here is, even though this is limited to maybe a couple amps maximum on its direct output, the switching can handle a lot more. You can get 10 amps switching and it doesn't affect the internal vibrator because it's another isolated circuit running that. So it acts like a mechanical transistor and actually gives you a few switch prompts at 60 hertz, where you could literally even switch a 12-volt battery into a big coil at 60 hertz as its own isolated circuit on the side. So again, not making any claims or anything, this is highly simplified, like I don't think Don Smith had it this easy, but it is an alternate approach to using spark gaps and things like that. And these were designed, like a motor. It's mechanical, won't last forever, but long lasting, because it was designed for military application to run equipment and everything. So think about it this way. How long has that motor in your garage, that old motor fan, been running? Still runs, right? So this could be a good approach to, at least experimenting with. It's not going to burn out overnight. So just thought I'd give you a update of where I am with the experimentations. And until next time, folks,